Hello guys, I hope you are all doing all right. Welcome back. So in today's session, I would like to talk to you about something quite important in peridynamics. And this is important because you will need this in order to be able to derive other material models using the peridynamics framework. This is the Frechet derivative. So I hope I can finish all the topic in this only one session. Otherwise, we will have to divide this in two parts. But let's get started. So guys, before I start, I would like to uh, let you know that during this session, hopefully only one, we will see a lot of symbols and terminology that is quite employed in peridynamics mathematics. And why is this important? Because you need this to derive material models. But I advise you to also not be scared at all, because this is the operations performed here are quite simple, are just summation and multiplication and so on. And if you have a clear concept of already of what is a derivative, that would be very, very helpful to in this session. Okay. The other thing is that if you don't understand the notation that is being employed here, such as the underlined vector states here, I would strongly advise you to go to the first video tutorial of peridynamics to see the meaning, in which I clearly or better explain what this terminology means. Okay. So imagine you have a function psi, which is dependent on a vector state quantity called A. Yeah. And then you would like to see or to understand in this case how much this function would change by making modifications to its internal parameters. So in this case, A. And this can be mathematically represented by adding to this vector state A and quantity an increment, which is defined with this symbol here, delta. So this is a very, very small increment in that parameter A, right? And if you manage at the end to, after doing this operation, to express your function as your increased function as your initial function only of this A, plus some other function here, which is being multiplied, this is why the dot product, times this increment that you defined earlier, then by definition, this parameter here it's called the Frechet derivative. Okay, Frechet derivative. And this, in this case, we are employing here the nabla operator. Well, this is a very wide known operator because it indicates a gradient of the function with respect to one of its components, which is vector state A. So now, if you want to measure how much the function changed when adding this parameter, then you simply decrease this term here from this other, right? So you have phi of A plus delta A, yeah, minus phi, this term here, phi of A, will give you the increment, the function increment of delta, which this is the remaining part, which is this Frechet derivative called gradient of the function times the increment, and some other larger terms, other smaller terms, I'm sorry, function of the magnitude of this increment that you added. Yeah. So what does this mean using a practical example? Perhaps this way it will be easier to understand. So imagine you have the function phi, which depends on the deformation state y, and this is defined as y dot y. Okay? Okay, now the first step is that you want to measure to know how much this function phi changed by increasing some parameter delta to its internal components. Yeah. So here you have it. Y plus some increment will be equal to this function, y plus increment times y plus increment. All right. Then if you develop this expression here, you will, this one with this one, we will provide you this part, and then this one with this one, and because you have also this one times this one, it will give you the 2 times y dot delta y plus, and then finally this with this parameter will give you this last expression here, right? And then you can see from here that you got the expression y dot y, which is the same initial function. Yes. So you can see here how you can compute the function increment. So you, this one, you get this part minus this part here, and this is expressed at y dot y minus y dot y because these are both the same, they are cancelled, and then you are left only with this other part here, 2y dot y plus some increment here, right? Increment times increment. And now, because we know from the definition that everything that is being multiplied times the increment, the function to the left that is being multiplied times the increment, it's going to be called, it's going to be the Frechet derivative. Then we know that the Frechet derivative, it's this term here, which is the left alone. And this Frechet derivative may also be expressed as the gradient of this function with respect to now y instead of the vector state a, because we are here adding to the function y. Yes, and this terminology means the same as this one here, because you can, instead of using the nabla operator, you can instead use partial derivative of c with respect to y, and this will be equal to this part. All right. So now, using something more ad hoc to what we are looking for. So let's say we have a function, and in this case, this is a peridynamic function. This is the bond extension, and the bond extension by definition is defined by the norm of the current position minus the initial position. Yes. So now, how can we start to get the increment and the increment of this? Okay, you have every time you see the y, you add the increment, and because x doesn't contain y, it stays the same. Okay, and now if you want to compute the increment, it will be this here term here minus this term here, which is what we have written here. But because we have x negative and x positive, they both will be canceling each other, and then you will be left alone with this part. So notice here that because opposite to the other example, here it was the function increment was being multiplied by an increment on the deformation, but here we don't have any other term. Yes, so therefore this is only the function increment, and this does not has a Frechet derivative. Yes, but let's consider now this other example here, and this is some other peridynamic function which is called the the dilatation, and it is defined as 3 divided by m. M is the weighted volume, which if you don't know about it, it is defined as omega x dot x, but we will not be looking at this for the moment. This is for you a constant in this particular case, omega x dot e. Yeah, and now you want to check how much the dilatation would change with a small increment in the bond extension E. So again, you apply here the same principle. You have the function, and everywhere you see a bond extension, you add an increment as it is in here. Yeah, if you develop this expression, you will end up with 2 terms. And this one, and then, you can compute the function increment by having this term, this whole expression here, minus the original function, okay? And this is what we are exactly doing here, because this term is exactly the same as this other term here. Both will end up canceling each other, and that's why you end up with this term here. So I had some issues with the camera, but now everything is solved. So we were saying that here, notice that in this case, the parameter, the function, this here, it's called the Frechet derivative. And why is this the Frechet? Because as we were mentioning before, if it's being multiplied times an increment, as in here, yes, times an increment, yeah, this term here will be called the Frechet derivative, and this is what I am explaining in this part below. Yes, opposite to the previous case, where in the bond extension, when computing the function increment, it was not multiplying by anything. That's why this is just an increment, okay? So this is the end of the road, meaning, whereas here, this is still multiplying the increment in the bond extension. Yes, and again, the Frechet derivative, this terminology, would be equivalent as expressing the partial derivative of the dilatation with respect to the bond extension here. All right. So now, one last example before we start the good part. So we have here the definition of the bond extension, the deviatoric bond extension. And the deviatoric bond extension is that bond in which is such a bond in which you take out from it the volumetric expansion. And the volumetric expansion, we know that it's being defined by theta. So in a similar way as in classical theory, you have the bond extension and you take out the volumetric expansion as defined as in here, theta x divided by 3. So now we can compute the increment in the deviatoric bond extension by applying an increment to the bond extension here, E, as it is displayed in here. And why we are adding an increment in E? Because we know that the bond extension E depends on the deformation state Y. So everything that it's dependent on Y, we are always applying that increment. So we have to remember that rule. Minus x over 3. X is not dependent on y, neither 3. In fact, they are both constants, so that's why they are put inside outside here. And then you are applying an increment again on theta. Why? Because we know that theta depends on e, and e depends on y. So this part stays the same. X over 3 stays also the same, and we know that the increment of theta can be expressed as here. But since the increment of theta, it's 3 over m over times omega x is the same as the Frechet derivative of theta with respect to e times the increment, so meaning that this is equal to to the Frechet derivative of theta with respect to E times the increment of E, then we can simply substitute that part into here. And this is what we are doing to get the function increment, sorry. So now, going into the interesting part that matters to us. Okay, why we did, wait, one more thing here before going into that. So we have here the property of the Frechet derivative. So if a Frechet derivative, to compute the Frechet derivative of some function phi that depends on of an inner product of an inside function psi, and this psi still also depends on a, then we know that we have to apply the chain rule, right? So we need to compute the derivative of this first function times the Frechet derivative of this inside function, right? And this would be equivalent as saying partial of phi with respect to c, and then multiplied by the c, the partial of c with respect to a. So it's just a matter of a property, as we know. And now what I was trying to tell you, and this is what really is interesting for us, is the following. In classical mechanics, we know that we have a strain energy density defined by omega, and this function is a scalar, right? And if you apply the derivative of this strain energy density function omega with respect to a strain, in this case, let's call it epsilon, we can obtain a stress. I'm just going to be, as a matter, just to be general, call it sigma here. Same way in peridynamics, if you have the strain energy density function and you apply the Frechet derivative with respect to the deformation state y instead of a strain, remember we are only working with the true deformations instead of strains, you will get the force state. And this is what we are trying to obtain in here. So in 2007, Sealing proposed this strain energy density for a peridynamic model called the linear peridynamic solid. By its abbreviation, I am writing it as here. And the first part looks over the bulk side, the volumetric part of the force, and the second part here looks for the deviatoric part of the force. Okay, and this meaning K here is the bulk modulus, and alpha is another parameter which will be related with the shear modulus. In this case, I'm calling it G. Then what it will follow here will be a matter of applying the increments to the theta, to the function theta, and to the function, the deviatoric extension D, and this in order so that at the end we can put as a common factor the delta or the increment in the bond extension. That's why we're doing this, because remember that we are trying to get the Frechet derivative of these terms times this. We know that everything that is on the left-hand side of this will be defined as the Frechet derivative of the omega, and because it's the Frechet derivative of the omega, then this means that we will end up having the force state, which is what it's really interested to us, right? So I will not go into deeper into all the details about this substitution, and so if you want, you have the slide here and you can have it a look upon it. But just important things is here you apply the derivative of theta, because theta is being to the square, then 2 with the 2 cancels, then you apply the increment, and we know that the increment is defined as of theta is defined as the Frechet derivative times the increment, plus here you have alpha over 2, but we know that the increment in the omega ed dot ed will be the Frechet derivative will have a 2 here, which will cancel with this one here, with this 2 here, and that's why we will end up with here, right? And after that, it's just a matter of, as I said, about substitutions. For instance, here you are substituting over increments all over the increments here. Then here, from here, this step to this step, you are just putting all the common factor delta E outside of the function. This is what we are wanting at the end. This is why it is being done so far like this. And then you are grouping these Frechet derivatives here into this part as it is in here, right? Then you make the substitution of the Frechet derivative in here. This term stays the same. And then you are again substituting this part, the deviatoric spot extension, by its definition, the extension minus the volumetric part, and so on. Then this term here, you will group it together and make some substitutions and so. And the important thing here is that omega x dot x is defined as m, the weighted volume, which is exactly the same as this one here, and that's why all this term you will end up canceling, and that's why you end up only with this final expression here, which is the definition of the force state for the linear peridynamic solid. And this expression here is the most commonly employed in the peridynamics material modeling when you want to employ different Poisson ratios and so. And why is that? Because you have the bulk modulus and the shear modulus both acting on the same. Okay. So guys, I hope you enjoyed this video and I did not bore you so much with the mathematics, but they are quite important to understand this in order to derive other material models, as I will do in following videos. Please guys, help me out by subscribing to the channel and give it a like to this video, and see you next time, okay? Have a good day. Bye bye.